We went through Newton's law of motion in the previous lecture. We went through the drawing of free body diagram, and though we didn't discuss them in details, we briefly went through a list of forces you will typically face again and again in this course. Since we will be dealing with these forces again and again, let us now spend some time going through them one by one in details. Furthermore, to put them in context, we will go through these forces as we are attempting to solve a real physics problem. The question is, a man applies 100 Newton force to pull a 10 kg crate at 30-degree angle as shown in the image. If the coefficient of static friction and coefficient of kinetic friction between the crate and the floor is 0.5 and 0.3 respectively, compute the acceleration of the crate. Do read this question a few times, take note of the quantities provided. The question asks for the acceleration of the crate. Hence, though I will not show the questions anymore in subsequent slides, I will draw the free body diagram of the crate progressively. So without further ado, let's start with the most obvious force, the pulling force applied by the man. This force is depicted by the red arrow on the crate's free body diagram, forming an angle 30 degrees with the horizontal. This force is 100 Newton in magnitude as given in the question. What makes this force just a little bit, complicated to handle is the fact that it's making an angle with the horizontal. The reason is, well, the moment you read this question, you might have anticipated the crate to move along the horizontal ground. I mean, you don't expect the crate to float around in some complicated fashion, do you? That means the acceleration of the crate you are asked for is likely to be the acceleration along the horizontal. At this point, you should have realized that you will have to resolve the pulling force along horizontal and vertical component, because when you need to compute the horizontal acceleration, only the horizontal component of the pulling force contributes to the computation. So you recall those sine and cosine to resolve the pulling force along horizontal and vertical component. We have done this a couple of times by now. Once you have resolved the force, you are no longer dealing with one pulling force F, but two perpendicular forces Fx and Fy, which are the resolution of F on the free body diagram. That's why I erased the diagonal force F from the free body diagram so as not to confuse ourselves later on. In the exam, when time is limited, this seems like a wasted move, draw then erase. With practice, you will get used to drawing Fx and Fy directly on the free body diagram. Next, every object on the surface of Earth experiences gravitational force from the Earth. In essence, this force comes from the attraction between two massive bodies. In the same sense as positive and negative electric charge or north or south magnet attract each other, two massive bodies also attract each other. The difference is, in the former case, two charges or two magnets of the same type repel each other. In the case of gravity, there is no such thing as positive or negative mass, at least not in classical physics sense, and it is always attracting. The two red arrows depicting the gravitation attraction on each other are action-reaction pair. This may sound weird to you, but as you are listening to this lecture through your PC or tablet, there is actually gravitational attraction between you and your PC or your tablet. The magnitude is just so very small and insignificant as compared to the gravitational attraction between you and the Earth, which on daily conversation you refer as wave. The magnitude of gravitational force put down also by Isaac Newton is given by F equal to G m1 m2 over r square. It is proportional to the mass of the two bodies m1 and m2 and inversely proportional to the square of the distance between the center of mass of the two masses. The proportionality constant is denoted using capital G, whose value is given by 6.67 times 10 to the power of minus 11 meter cubed per kilogram per second square in SI unit. We have learned how to deduce the SI unit of gravitational constant in lecture 2. Now, how all this information got to do with our problem at hand? Well, the crate experiences gravitational attraction. Direction-wise, it is pointing toward the center of the Earth, which means on flat ground like this, it is pointing down. It is denoted using capital W, which stands for, well, weight. The magnitude is then given by Newton's equation for gravitation, after you substitute m1 for mass of the Earth and m2 for the mass of the crate, and r for the radius of the Earth. Since the crate lies on the ground, which is effectively on the surface of the Earth, the effective distance between the crate center of mass and the Earth center of mass is the Earth's radius. At this juncture, you can simply plug in the numerical values of each quantity and you will get your answer. But wait a minute, how many of us are rocket scientists? In most case scenario, As far as daily necessities are concerned, aren't we dealing with objects on or very near to the Earth's surface? Even if you are considering your weight when you are flying on board of 747, isn't it merely an additional few thousand meters to the denominator of the equation? After all, you don't get noticeably lighter on board of the plane, do you? What I'm trying to say is, as far as daily mechanics are concerned, which is what this course is concerned about, it's worth computing the value of g, me, and re square in advance. And when you do so, abracadabra, you end up with the gravitational acceleration. Thus, from Newton's gravitational law F equal to g m1 m2 over r square, we just derive the equation for weight W equal to gm or mg. When we went through lecture 4 on kinematics, we learned to call g gravitational acceleration because any falling object experiences this acceleration. Now, in light of Newton's second law, we learned that 1. What causes the object to fall is gravitational force. 2. If we are comparing term by term between F equal to ma and W equal to mg, we should immediately notice that g takes the role of a in Newton's second law. A is acceleration, hence g should also be some kind of acceleration. It is acceleration due to gravitational force, and hence the name gravitational acceleration. 3. The equation W equal to mg provides another way to define mass. In the last video, I presented mass as a ratio between the amount of force applied to the acceleration of the object. Experimentally, that means if you apply a known force to the object, you observe how the object gains speed over time, then you take the ratio between the two, the answer is the so-called inertial mass of the object. In the second method, now you first weigh the object, bring it high up, release it, and observe how it gains speed as it is falling. The ratio between the weight to the acceleration will give you the so-called gravitational mass of the object. Though they are fundamentally measured in different ways, as far as physicists are aware, there has not been found any difference between inertial mass and gravitational mass. And 4. As far as near-surface motion is concerned, g is constant because it is made of quantities which are more or less constant, namely Earth's mass, Earth's radius, and gravitational constant. But as you might have guessed, this value will be different on different planets. If you are dropping a ball on the moon, for instance, the acceleration there is going to be noticeably smaller. And for that reason, if you have seen those footages from Apollo mission, everything seems to go slow motion on the moon. Some of you may also be wondering, since g actually depends on the distance from the center of the Earth, how far above the Earth's surface the value of g could still be considered constant? Well, it's rather hard to say actually. I mean, there is no clear-cut definition when we can or cannot use 9.81 meter per second square. For if we plot the Earth's gravitational attraction against distance from the Earth's center, it will look like this. It decays exponentially because of the inverse square of the distance. Having said that, as I mentioned earlier, an additional few thousand meters above sea level will not affect g much. You can easily guess from the context of the problem whether to use F equal to g m1 m2 over r square or W equal to mg. For your information, our Earth is not perfectly spherical, so the radius of the Earth at the poles are slightly shorter than the radius at the equator, which implies that you are actually experiencing higher g and slightly heavier when standing at the poles than you are on the equator. But let's don't bother with this minuscule detail. For simplicity, we shall assume the Earth to be a perfect sphere. We thus established so far that the weight of the crate is 98.1 Newton. Meanwhile, the pulling force contributes an outward force of 50 Newton. It is clearly shown that the downward force is larger than the outward force, which means that the crate should stay on the ground. It is not going to float up. At the same time, because it is lying on hard solid ground, it should not sink in either. Overall, the crate should stay at equilibrium as far as vertical motion is concerned. That is to say, the crate is not moving along vertical direction. Pay attention to the last phrase, okay? I'm not saying the crate is not moving at all. I'm saying that the crate is not moving along vertical direction. This means that the net force along vertical direction has to be zero. I use capital R, which stands for resultant, to refer to the net force. The subscript indicates that I am talking about the vertical or y component. At the moment they are not, as the downward force is obviously larger than the upward force. This points to the existence of the third force, a force which has to point outward perpendicular to the floor to balance the weight. This force is called normal force. normally denoted using capital N. Thereby, although it is not required to do so in this problem, we can compute the normal force 48.1 Newton. Pay attention to the signs. Forces are vector quantities. Their direction do matter. Normal force and the vertical component of the applied force are pointing in the same direction, and hence they share the same sign, which is positive in this case. Weight is pointing in the opposite direction, hence it carries the negative sign. Were we to assign the negative signs to the normal and vertical component of the applied force, the weight would have to carry positive sign. The rest of the algebra and the final answer remain the same. Lastly, before we are moving on to the next force, I just want to explain why this force is called normal force. A student rather innocently asked me before, if this force is called normal force, what are considered abnormal force? Well, let me point out that I'm not referring to normal as being ordinary versus weird. Not in that sense. The term normal in mathematics means perpendicular. Normal force is always perpendicular to the contact surface. By showing that the normal force is non-zero, we have thus far established the fact that the crate is in contact with the floor. The pullman has to drag the crate across the floor, and there is going to be friction between the crate and the floor. What will be the direction and magnitude of this friction force? Well, direction-wise, it has to oppose the direction of motion of the crate. If the crate is being pulled to the right, the friction force will have to point to the left. In our case, the man pulls the crate to the left, hence the friction has to be pointing right. Magnitude-wise, it has to be proportional to the contact force between the crate and the floor. Think about it. If this crate is floating in the air, that is to say there is no contact with the floor, obviously there won't be any friction either. On the other hand, the more grounded the crate is, the more the man has to drag it. Whether the crate is floating or not, this is depicted by the normal force, isn't it? In short, how much grounded, so to say, the crate is, it is given by the normal force. Hence, friction force has to be proportional to the normal force. The proportionality constant will then has to depend on the type of surfaces in contact. Obviously, dragging the crate across an icy surface, a marble tile, a parquet floor, or an asphalt road makes difference. This difference is captured by what we call coefficient of friction, denoted using the Greek letter mu. It is also a dimensionless or unitless quantity. In short, F equal to mu n, that's the equation to compute the friction force. Now there are two types of friction, and hence two types of coefficient of friction. One is called static friction, denoted as Fs, which involve coefficient of static friction mu s. The other is kinetic friction, denoted as Fk, which involve coefficient of kinetic friction mu k. The subscript s and k are used to indicate static and kinetic friction respectively. Why are there two types of friction? Why so complicated, you may ask me? Well, have you ever pushed or pulled something heavy in your life before? If you have not, try to do so on the nearest furniture around you. Cupboard, bookshelf, bed frame, etc. If your parents or sibling ask you what on earth you are doing, tell them that you are studying physics. Try to push or pull those furnitures. You will soon realize two things. One, if the furniture is too heavy for you, you may not be able to move it despite of the force you applied. And two, let's say you are capable of moving it, you will need to apply higher force, like you have to jerk it up at the beginning to get it to move. But once it moves, you no longer need to apply that much force to push or pull it. The former case, when you are unable to move the cupboard, show the static friction at play, because obviously you are applying the force onto the cupboard, but the fact that the cupboard is unmoved shows that the net force acting on it is zero, which further implies that there is another force opposing yours, friction force. It is called static friction force because the friction acts while the cupboard remains unmoved or static. Furthermore, static friction will also vary in accordance to the applied force. When there is no applied force, of course there won't be any friction. The moment a pulling or pushing force is applied, the static friction will instantaneously act, having the same magnitude but opposing the applied force. The resultant is a zero net force and the cupboard remains static. You apply larger force, static friction will also increase accordingly, all the way to the point where the static friction reaches its maximum as given by mu s times normal force. If you are then able to provide slightly even just a bit more force, the cupboard will start to move because the applied force is no larger than the maximum static friction force, and the cupboard will experience non-zero net force as a result. The moment the cupboard is moving, static friction is no longer at play. Instead, kinetic friction will be at play. It is a more or less constant force given by mu k times n. So do note, kinetic friction is always given by mu k times n, but static friction is not always given by mu s times n. It varies in accordance to the applied force, with maximum value provided by mu s times n. For that reason, it always takes more force to get something to move first, and lesser force is required to sustain the motion subsequently. Back to our problem. The values of the coefficient of static friction and kinetic friction mu s and mu k are given as 0.5 and 0.3. For a reason I just explained, the value of mu s will always be larger than mu k. Since we have computed n in the previous slide, we can immediately compute the maximum value of static friction Fs max and the kinetic friction Fk, which are 24 and 14.4 Newton respectively. Next, the applied force along the horizontal component Fx is 86.6 Newton, which is way larger than the maximum static friction. That means the static friction will not be able to prevent the man from pulling the crate. The crate is moving, and immediately the kinetic friction is at work. Hence, the resultant force along the horizontal component is obtained by subtracting the kinetic friction to the applied horizontal force. That is 86.6 minus 14.4, which is equal to 72.2 Newton. So far so good. Before we move on, let's have a closer look at the nature of friction force. What causes friction to happen? From this diagram, it is clearly seen that friction originates from uneven interface at microscopic level. This uneven surface at microscopic level is formed naturally. Sometimes you may be presented with a problem where you can assume a perfectly or an ideally smooth surface, and hence you can ignore friction. Such problems only appear in textbook as there is no such thing as a perfectly smooth surface in reality. You can of course attempt to reduce friction by applying lubricant oil in between the two surfaces. By doing so, you are actually trying to prevent the two relatively rough surfaces from dragging against each other. Or the next time you see those girl band or boy band posters such as this one, and you wonder how to make your skin as smooth as how theirs look like, forget it, it was Photoshop. Under the scrutiny of microscope, you will soon see the true nature of human skin. No amount of cosmetic or beauty soap will be able to help you. Finally, we are ready to solve the problem. Compute the acceleration of the crate. We have computed the relevant forces. We shall not expect the crate to move along the vertical direction, which means the net force along the vertical component is 0. That's how we managed to compute the normal force. However, there is a net force along the horizontal component. From Newton's second law, this net force contributes to the acceleration of the crate along the horizontal component. We can thus compute this acceleration given by 7.22 meters per second square to the left as shown in the diagram. So that's it. I hope this simple exercise can give you some exposure to problem solving using Newton's second law. Though I admit that this is the simplest kind of problem. What happens if the crate is placed on a ramp, or if multiple objects are involved? These problems will be the subject of our in-class exercise.